Hello students, we will continue from where we had stopped in the first video, that is case 1. We will start with case 2, which says determination of elevation of the object when the base is inaccessible. This is very important, that is the base of the object is inaccessible to us. That means we cannot reach to the base of the building or base of the tower, whatever you take it. Yes. And the instrument station is in the same vertical plane as the elevated object. So if you consider the vertical plane of the object, the instrument stations are in the same vertical plane. This will be clear when you see the diagram. Under this case 2, we have two more cases which says the first one, instrument exists at the same level and instrument exists at different levels. Now the very important thing in this particular case is when the base of the object is inaccessible to us, we will have to use two instruments, or we will have to shift the first instrument to another position. So basically we will have two instrument stations. Okay, this is in case 2 when the base is inaccessible to us. Now there are two cases which I said, that is the instrument exists at the same level and instrument exists at different level. Means when we place two instruments, the height of both the instruments is same in first case and the height of instrument in both the second case is different. So if you see the diagram here, this is the first case wherein the instrument exists at the same level. So this is our vertical object, that is FA. So the base of the object is inaccessible to us as there is a elevation change. The terrain is a different terrain, so we cannot measure the horizontal distance from any point, otherwise it will be an error if you measure. So the base of the object is inaccessible to us. So that is the reason we have two instrument stations. First instrument is instrument O1 and second one is O2. Now for our convenience, we have dropped the base of this vertical object to A dash and to till the horizontal line of sight, that is till the center of the instrument. So now we have two instruments, instrument at O1, instrument at O2. The vertical object is FA and we have a staff kept at the benchmark which has a reading S. Now when I say the axis is at the same, the instrument axis is at the same level, this means the horizontal line of sight is same for both the instruments. That means this value S or the backside on the staff reading kept at benchmark is same for instrument kept at O1 and at O2. Theta 1 and theta 2 are the vertical angles made by instrument at O1 and O2 respectively. Now again, as I said, we are going to use a trigonometric concept to solve or to get the RL of point F. We will be considering two triangles. One is F O-2 A dash and F O-1 A dash. Now I am using O1 dash and O2 dash as we have to consider the center of the telescope or the center of the instrument. O1 and O2 are the ground points of the instrument station. So I am using O1 dash and O2 dash as the center of the instrument. So here O1 and O2 are instrument stations. O1 dash and O2 dash are center of both the instruments. H, theta 1, theta 2, S, and okay, I forgot to explain what is small d and capital D. So from the diagram here, capital D is the horizontal distance between the first instrument station and the base of the vertical object, and small d is the difference or horizontal distance between O1 and O2. So here it is marked in the diagram. So it is very clear that small d and capital D are basically the horizontal distances between the instruments and between the instrument and vertical object respectively. Now again, to get the RL of point F, we will have to use trigonometry for two triangles, and using tan of theta for first triangle and for second triangle, we will be able to get what is H, and then from there we will be getting the RL of point F. So to go ahead, first from triangle O1 dash A dash F, that is O1 dash A dash F. So we will be using this triangle first, which is O1 dash A dash F. In this triangle, if I write it as tan theta 1, okay, if we take tan of theta 1, it is opposite upon adjacent. So it will be f a dash divided by o1 dash a dash. So tan of theta 1 is f a dash and o1 dash a dash. So again, this is from the diagram. We can write it as small h divided by capital D. So here tan of theta 1, I have written it as f a dash upon o1 dash a dash, o1 dash a dash, and theta 1 can be written as h upon capital D. So from here h is equal to d tan theta 1. So this is from one triangle. Similarly, if we take the second triangle, which is O2 dash A dash F. Second triangle is O2 dash A dash F. We take tan of theta 2, which is again opposite upon adjacent. Opposite is small h, that is F A dash, and adjacent will be O2 dash A dash, which is equal to small d plus capital D. So tan of theta 2 is f a dash divided by o2 dash a dash, and tan theta 2 will be h upon capital D plus small d. So here h is equal to d plus d tan of theta 2. Now from equation 1 and equation 2, as the left hand side is same, we can equate it and we will get the equation or the value for capital D, which is unknown. As I said, the base of the object is inaccessible. That is the reason we cannot get the horizontal distance between the instrument station 1 and the base of the vertical object. We can very well get small d, as both the instrument stations will be very close, or we can choose the instrument station accordingly to get the value of small d. So here capital D is unknown to us. So it is equal to d. Just make a solve this, simplify this expression and get the equation for capital D, which is equal to small d tan theta 2, tan theta 1 minus tan theta 2. Now theta 1 and theta 2 is known to us, as we are going to get that from the transit theodolite. We are going to cite a point F, which is shown in the diagram, and we will find out, or we will get that theta 1 and theta 2 from the instrument. Small d can be calculated by measuring the horizontal distance between both the instrument stations. So from here we will be able to get the horizontal distance capital D, that is the distance from the first instrument station to the base of the vertical object. Now we also know that h is equal to d of tan theta 1. So from equation 1 we can again get the value for h. Therefore h is equal to d tan theta 1. So I am substituting the value of d. So we will get this particular expression. Now to get the RL of point F, again we are writing RL of point F is equal to RL of benchmark plus S plus H. We have already written this equation in case 1. Again I will just explain this to you in the diagram. So to get the RL of point F, it is RL of benchmark plus S in the same line of sight plus H. So we get RL of point F. I'll just explain it to you again. RL of benchmark plus S plus H. We get RL of point F. Now we have derived the equation for H. Therefore, the final RL of F will be equal to RL of BM plus S plus the equation for H, wherein D is known, theta 2 is known, theta 1 is known. S also is known to us, as it will be a backside reading on the staff kept at benchmark, and RL of benchmark should be known to us. Okay, so this is the first case wherein the axis of the instrument is at the same level. That means the backside on the staff kept at benchmark is the same reading S from O1 and also from O2. Now going to the next case wherein instrument axis is at a different level. Again this particular case is subdivided into two more cases. The first case is instrument axis at O2 is higher than at O1, and instrument axis at O1 is higher than that of O2. So if you see the diagram, this will be more clear to you. When instrument axis at O2 is higher than that of O1. So if you have an unequal terrain, You cannot keep both the instrument at the same axis. So this is the second case wherein horizontal axis of O1 is different than horizontal axis of instrument station O2. So now the two cases under this is O2 is lower than O1. O1 is lower than O2 and O2 is lower than O1. These are the two different cases. So in that, this is the first part, that is A, instrument axis O2 is higher than that of O1. So basically first is the instrument axis of both the instruments are different. Okay. Under that, the first case again is O2 is higher than O1. So this, we will consider this case first and then we will go to the next one. So if you see the diagram, it is again very simple. FA is the vertical object. We have to calculate the RL of point F. We are using two instruments to get the RL of point F, as the base of the vertical object is inaccessible to us. Now this is O1, this is O2. Again vertical angles θ1, θ2. The readings on the staff kept at benchmark from both the instruments will be different. So we are taking it as S1 and S2 respectively. So S1 from O1 and S2 from O2. Similarly, the height taken from the first instrument station is H1 and second instrument station as H2. So we have a small projection of FA vertical object by A dash, A double dash. Okay. Again, this remains the same, small d and capital D. This is the explanation that is given on the new terms that we have used in the diagram, that is H1, H2, S1, S2. So S, capital S is the difference of S2 minus S1. So from this figure, we can write S1 minus S2 equal to S, which is equal to A dash, A double dash, again which is equal to H2 minus H1. So from the figure, we will be able to write H2 minus H1 is equal to A dash, A double dash is equal to S1 minus S2, which is equal to S. This is clearly seen from the diagram itself. Okay. Now again considering two triangles. F O1 dash A double dash. Okay. F O1 dash A double dash. We will write the equation for tan of θ1. Again using the second triangle F O2 dash A dash. We will write equation for tan of θ2. So from triangle O1 dash A double dash F, tan of θ1 is equal to H1 upon D, and from triangle O2 dash A dash F, tan of θ2 is equal to H2 upon D plus small d. So H1 is equal to D tan θ1, H2 is equal to D plus D tan θ2. These are the two equations which are derived using the trigonometric concept. Kindly refer to the diagram and consider the respective triangles and try to write the equation for tan of θ1 and tan of θ2. This is a very simple concept which is used. Now next we subtract equation 2 from 1. So we write H1 minus H2, which is equal to D tan θ1 minus capital D plus small d tan of θ2. Again H1 and H1 minus H2 can be written equal to S. From here we know that H1 minus H2 is equal to S. So I write it equal to S and simplify the equation, and we get finally the value for capital D, that is equal to capital S plus small d tan θ2 upon tan θ1 minus tan θ2. So as D was unknown to us in the diagram, as the base of the vertical object is inaccessible, here we have got the equation to get the horizontal distance between the base of the vertical object and the first instrument station. So we have got capital D here. S is known to us, small d is known to us, θ1 and θ2 is known to us. Now from equation 1, again we know that H1 is equal to D tan θ1. Substitute the value of D in this. So we get H1 equal to this particular equation. Now to write the RL for the point, RL of point F is RL of BM plus S1 plus H1. Now, why it is